This is OS project presentation topic number 8, which is Virtual Memory Management Replacement Algorithm OPT and LRU. We are group 11. Our team members are Jin Leong Chen and Lin Kai Rong. So the first thing we hop on is the real world scenario. Modern smartphones had limited physical RAM, like for example 4 GB to 8 GB, but run resources heavy apps such as game, AI model, and also social media. The problem are what happens when the user open more apps than the RAM can hold. So the OS must avoid an existing app to make space, which is called page replacement. So what will happen to this? So the best decision will happen is select and reload, and then the good decision that can happen is smooth multitasking if the thing is work properly. So the goal from here is simulate this decision making process to find the most efficient strategy. So there are two algorithms we're going to compare. The first one is OTP, and then the second one is LRU, which is optimal and least recently used. So the strategy, logic, feasibility, and role are work different here. So the strategy for OTP is look forward, which is looking at the future, and then for the LRU is look backward, which is looking for the past. So the logic here is if the ad will not be used for the longest time, which is for OTP, and for the LRU is evict the ad that hasn't been used for the longest time. The feasibility for OTP is impossible because it requires predicting the future, so which cannot be applied in the real world scenario. And then the LRU is practical because it can use history to predict the user future. So for the role, the OTP is theoretical benchmark because it is not realistic, and then the LRU is the most practical one, which has the real world standard. System architecture. So the core logic here at the back end is we are using the language C++. We use a standard vector for frame and standard mat for history tracking. Ensure the mathematical accuracy for page fault calculation. So for the visualization, which is the front end, we use the language HTML5 and JavaScript. So portal language for dynamic and real-time animation. Visualize the scanning process. For example, green for hit, red for miss. Relationship between diagrams. As you can see here, we have the page manager at the main system, and also he managed two, which is OTP and LRU. For the page manager, as you can see the element here, we have frame vector, capacity which is integer, page fault with also integer, and then page hit which is also integer. The function are page manager is hit, add page, remove page, get frame, and then display stat. For the OTP function here, we can see there is run OTP, which is serves as a function, and then get OTP victim, which has need the input of frame, reference, the string, and also the current index, and then he return the integer. So for the LRU here, we has the last he has more element than the OTP, which is the last usage. So the function here we can see is a run LRU, which is as a function, and also get LRU victim, which serve as a get back the value. And then the simulation result here for the OTP, we input the string as 70120304230321201701 as an example. As you can see here, in the UI, we put the referencing inside the box, and then we can adjust the RAM slot to 3 to 5 to 4 even to 10. So we run the OTP result here. As we can see, here is the input we have, and then this is the result 701, which is 701 if we from up to down. This is OTP result. And then the next one is the LRU. So we put the same input here, and then we set the RAM slot to 3, and then we run the LRU algorithm. And then this is the input, and then the outcome is 107. The fault is 12, and then for the previous one, OTP is 9. And then the hit is 11, and then the hit for this one is 8. So this is a simulation result. OTP has 9 fault and LRU has 12 fault. Why? Why didn't the OTP win? It's simple, because OTP cheated. It see the future, it can make the perfect decision every time. It hold onto page that will needed soon, and kill page that won't be needed for a long time. It represents the mathematical limit of efficiency. Why didn't the LRU come so close? LRU rely on the principle of logicity. This principle stated that computer programs are repetitively. If you use app A just now, you are statistically very likely to use app A again in the next millisecond, which is in the next future. So result, even LRU couldn't see the future, the past was an extremely accurate mate of the future. So, but still, we don't need to be clairvoyant, which is super ability, to be efficient. The simulation proved that we don't need impossible hardware that predict the future, which is OTP, to build a very smart smartphone. You just need to track the past, which is using LRU accurately, because the cost of profession is high. Gaining those last few points of performance, which is from 12 volt to 9 volt, will require impossible knowledge. And then the most important thing is the value of approximation. LRU get us 80 to 90% of the way to perfection by just looking at the history. In CS, a good approximation that works in real time is always better than a perfect solution that is impossible to build.
Hello, Doctor. My name is Liam Tyrong. I'm responsible to represent the visualization, addition, effect, and functional future work and conclusion part. For this part, visualization, addition, effect, and function, we're moving on to the user interface design. We want to ensure the simulation was just not a black box of numbers. We add specific visualization effect to provide an intuitive understanding of the algorithm status. We use distinct color coding to show hits and fails instantly. Green appears when a hit occurs, meaning the patch was successfully found in RAM. Red highlights a fail, visualizing the moment the system lags. This gives the user immediate impact regarding how well the algorithm is performing at any given second. So we come to interactive control. Beyond just watching color, we want the user to control over the simulation flow. We implement the reset and pause button. The pause function allows the user to stop the process mid-execution. This is crucial for educational purpose as it gives the user time to think and process why a specific number was just repressed before moving to the next step. The reset function allows users to restart the algorithm immediately if they miss a step or want to compare the two algorithms from the beginning. And we come to console. We implement the console log to complement the visual animation. While the graphical blocks show the current state, this panel allows the user to trace the entire history of activities. It records every decision the OS makes, which specific app was requested, whether it caused a fault, and exactly which victims was swept out. This helps the user trace the algorithm progress much easier and more intuitively. And we come to the future work part. While our current simulation is robust, there are specific areas where we can bring it closer to a real-world Android kernel. We have identified 3 key areas for future work. Simulate crowd algorithm. We plan to implement the second chance algorithm, which approximately LRU with less hardware overhead, making it more realistic for mobile kernel. Add ZRAM support. Modern phones compress memory instead of swapping to disks. We want to simulate ZRAM to analyze the trade-off between CPU compression and memory gains. Integrate low memory killer LMK. We will add an out-of-memory daemon that dominate background apps entirely when RAM is critical, simulating real Android behavior. Conclusion, OPT is the benchmark. The optimal algorithm achieves the lowest patch file, confirming it as the theoretical ideal, though impossible to implement in real time. LRU is the practical standard. With 12 file, LRU proof it is a high effective approximation by using the principle of locality. It successfully minimizes lag without needing to predict the future. RAM matter. Our simulation mathematically proved that a small increase in frame disproportionately improves stability, validating the need for higher memory in modern budget device. So that's all for our team, Lian Kairong and Qing Liu Group 11. Thank you, Doctor.